So today we look at pressure as a chapter, and we'll start with pressure in solids. With me here I have a certain solid. This is a cuboid measuring 6 by 10 by 32.5, and we are just going to see how pressure on this object behaves. So to start with, we need to find out what is this force that this object can exert on the ground. So the way it is actually placed on the ground is upright. This is actually it's standing upright, and at the same time we can still make it to lie on the ground like that. So the way pressure behaves in this case is not the same way pressure behaves in that case. Even if the object is the same, pressure exerted on the ground is not the same. So first of all, we need to know that pressure P is given by force over area. So force is supposed to be newtons and area in meters squared. Now that the mass of this object is 2.5 kilograms, we change the force into newtons by saying that force equals to mass times the acceleration due to gravity, and therefore the force will be mass is 2.5 multiplied by 10 newtons per kilogram, and the answer we get is 25 newtons. So when we substitute here, we find that force pressure P will now be given by the force, which is 25 newtons, over, we can see that the object is actually standing on a very small area. This area is 6 by 10. Remember, we have another area which is 10 by 32.5 and another one which is 6 by 32.5. We take the least area possible. So in this case is 6 by 10, which is the minimum. That gives us 60 square centimeters. And not 6 by 32.5. Also not 10 by 32.5. So our least area will be 6 by 10. Remember, these are centimeters squared, so what we do, we divide by 10,000. We divide by 10,000. So this is the same as dividing by 10,000. And this is actually just like saying 25 newtons over 6 multiplied by 10 to the power negative 3. After getting the force, which is 25 newtons, when we convert 2.5 kilograms into newtons, we get that. We now substitute, and since we said pressure is force over area, therefore pressure is 25 newtons over 6 times 10 to the power negative 10 raised to the power negative 4 is the same as dividing area by 10,000. That gives us 6 times 10 to the power negative 3 meters squared. Therefore, when we divide, we get 4,166.7 pascals. Remember that 1 pascal is the same as 1 newton per meter squared. It's the same, though the SI unit of pressure is pascals. So when we turn the object now to stand on the broader side of it, so that we maximize the area, we can see that it's standing on 32.5 centimeters by 10 centimeters side. This is the largest side possible. and therefore for us to get the least pressure, because at this time this object is exerting a very small pressure on the ground. That's why when you put your hand over here, you will feel lesser pain than when you put it under this other object. The same object but standing in a different manner. So area here is going to be 32.5 multiplied by 10, which of course gives us 325 centimeters squared. We change to SI units by dividing by 10,000, and the answer is it becomes 3.25 times 10 to the power negative 2. So this is meter squared, and pressure equals to force over area. Substituting, the force does not change, 2.5 kilograms simply remains 25 newtons over area, which is 3.25 times 10 to the power negative 2 meters squared. So the answer we get here is actually 769.2 pascals or newtons per square meter. So with me here I have a block, a metal block that is actually 2.5 kilograms, just to demonstrate when do we have the least pressure and when do we have the maximum pressure. So we're going to look at it. So here we have this piece of metal. This is actually 2.5 kilograms, and it's a cuboid, 6 sides. So this is the wider side, followed by this side, then the least area is this side. So when we place it on the ground this way, it's actually currently exerting a very low pressure. In this case, it's exerting only 769.2 pascals. And actually, when you put your hand down that way, you won't feel as much pressure as when you place it on top of your hand this way. This is so painful. So right now, it's actually exerting 4,166.7 pascals on this table. So that's the difference between least pressure and maximum pressure in solids. Now from this point we look at atmospheric pressure, and I'm going to just mention a few things like I think we understand that when we have a balloon, for example, hot air balloon, for this balloon to go up, it experiences some forces, one of them being upthrust force. We have the weight which is acting downwards. Then during that process, it's also experiencing atmospheric pressure. This is pressure due to the mass, that large volume of mass of air which is around it in that form. So this air is the one that exerts atmospheric pressure on the balloon. Now this pressure can be measured using a barometer, and a barometer simply consists of a few items, some of which are, we have the container that has mercury. This is mercury. Then we have a long tube of about a meter which is immersed inside there. Of course, there's mercury over here. So mercury is going to rise up the tube because of this pressure exerted on this surface, the top surface of the liquid. So this is mercury. Mercury is denoted as Hg. This is the short form or the symbol mercury. So due to this weight of air acting on the surface of the mercury, it forces it up this tube until a certain point. So what we do, if we want to know the atmospheric pressure of a place, then we measure the height of that place. So this is the height that we measure, h. So this height gives us the atmospheric pressure in terms of centimeters of mercury, written this way. So this is simply a tube. This is a vacuum, and here we have mercury liquid. Now from here, we are going to see what are some of these applications of atmospheric pressure, and we are going to use this mountain. This is a small mountain. This is a diagram, simple diagram representing a mountain. If we want to know how high this mountain is, then we use the same barometer to measure the atmospheric pressure at this base and also atmospheric pressure at the top there. Then we compare the two. First of all, before you find H, you're supposed to know what we call density. We need to know density of air, which is always around 1.25 kilograms for every cubic meter, and also density of mercury, which is 13,600 kilograms per cubic meter. Now, we are looking for H, which is the height of the mountain. We compare the pressure due to mercury in the barometer and also pressure due to air column around that mountain. So this is the formula that we use. We know pressure in fluids. Fluids include liquids and gases. So pressure in fluids is given by density times height times G. So pressure due to mercury, that is density of mercury, height difference due to mercury times G, equals to pressure difference due to the air column, which is density of air, height due to air column times G, where G represents acceleration due to gravity. So density of mercury, we've seen, is 13,600 times height difference. Here we know is 76, but as we go up the height, increase in altitude leads to decrease in pressure. That's why the pressure at the top is lower and higher at the bottom. So the pressure difference is 76 minus 60, which gives us 16, changed to SI unit, that is 0.16 meters multiplied by G. Equals to, on the other side, we have density of air, which is 1.25, times height of air column, that we don't know, which is the same as height of the mountain, times G. So when you solve everything correctly, you're going to have H as 1740.8 meters. So this is the altitude of this mountain. So this is one of the areas that we make use of atmospheric pressure. From here, now we're going to look at pressure in liquids. We've already done pressure in solids. pressure in gases, which is atmospheric pressure. Now let's look at pressure in liquids. On the board here, we have a cylinder containing a liquid. This liquid can be water or any other liquid. We can use this to investigate the pressure of this liquid that is being exerted on the ground inside the liquid. Now, suppose we take our height to be h, which is height of the liquid from the bottom to the level. From the solid, we know that pressure P equals to force over area, and we can express this in another manner by saying that pressure is mg over A. From measurement 1, we know that volume V equals to area times height. Therefore, A equals to volume over H. So if we substitute this one here, then we're going to have pressure P equals to mg divided by V over H. Working out that, we shall have P equals to mg multiplied by H over V. And we know that mass over volume is the same as density. Therefore, P is density. This is mass over volume times G times H. Therefore, pressure in liquids is given by that. So if you want to know the pressure exerted by this liquid here, then we take its density, multiply by the height from the ground, multiply by acceleration due to gravity. So this is the formula that we use. We're going to see some of the examples of pressure that is acting on liquids. So with me here, I have a liquid inside this. This is a syringe. This is another syringe. They're interconnected using a tube. So we can be able to transmit pressure from this side to the other side using this liquid. So if I exert some force here, focus on this empty cylinder. If I exert some pressure here, you can see that the other one rises. I can also do the opposite, where I exert the pressure here, a force here on this piston, and then on the other side we have the other tube rising. So simply the pressure is being exerted, transmitted from this side to the other side. If I'm exerting here, then pressure is exerted on this side and going to the other side. So let me repeat. The other side. You can see those changes. Okay, this transmission of pressure is actually governed by a principle called Pascal's principle of transmission of pressure, and it states that pressure transmitted in a liquid, in an enclosed liquid like this one, is transmitted equally to all other parts of the same enclosed liquid. So that is Pascal's principle, and it can be used in so many areas. We have the hydraulic press, we have hydraulic machines, they use the same principle. From here, we're also going to look at what we call a U-tube. A U-tube manometer is actually used to measure pressure of gases. It can be used to measure pressure in gases. So I'm going to project a simple manometer having a liquid so that we know what it can be able to do. With me here, I have a simple manometer. can see the liquid actually in the tube. Then we have a scale here. So without any difference in pressure, you can be able to see that the liquid is always at the same level. So whatever tube that you use, due to equal atmospheric pressure in both sides, left and right, the pressure is the same. We are going to have the liquid at the same level. But when I slightly increase the pressure on one side, I'm going to use this simple tube, fix it on one side, then I'm going to blow. You can see that the level of the liquid rises on the other side. I'm blowing from where the tube is, this side. You can see that effect. So for us to know the pressure difference, we simply get the difference in heights. Get the height on the higher side minus height on the lower side, then multiply by density of this liquid, which is colored water. So we shall just use 1000 times 10. So that's what happens. When I withdraw the pressure, you can see that the liquid goes back to the same level. This is because the pressure being felt at the tip of this tube is the same pressure acting on the open side of this U-tube. So this tube can be connected to a gas, for example, and if we find out that the gas actually pushes liquid to this other side up, then it means the pressure of that gas is higher than atmospheric pressure. When we connect and find that the pressure pulls this liquid up, this is the side connected to the gas, and it rises up, then it means atmospheric pressure is higher than the gas pressure. So I'm going to blow again, showing that the gas pressure is higher than atmospheric pressure. This is the case. Okay, in this other case, I'm going to suck, showing that atmospheric pressure is now higher than the gas pressure. So those are the two differences. So before you use the manometer to calculate the pressure of a gas, ensure first of all you identify which one is higher. Is it atmospheric pressure or the gas pressure? So let's look at some of the examples. So on the board we have two tubes which are communicating different informations. Here we have, okay, both of them are U-tubes connected to gas inlets. You can see here and here, gas comes in like that. You can see the first tube here pushes the liquid. This is actually water. It is water in both cases. Then it rises like that. But this gas is not the same as that gas. They could be coming from different sources. So let's say gas A, then gas B. So gas A actually pushes the liquid up the U-tube. That means its pressure is actually higher than atmospheric pressure because atmospheric pressure is acting over there. Therefore, here in this case we say that the gas pressure Pg equals to atmospheric pressure Pa plus the pressure due to the difference in heights, which is given by rho Hg. So this is the formula we use for this case. For this other case, we can see that the opposite is happening. The gas is connected over there, but then the atmospheric pressure acting at that particular point is pushing the liquid up towards the gas. What this means is that atmospheric pressure is higher than the gas pressure. So the formula that we use here is that pressure of the gas is actually atmospheric pressure minus pressure due to this height column, which is rho hg. So those are the two different equations that we use. So here, when we substitute, we're going to have atmospheric pressure roughly is about 100,000 pascals, plus density of water is 1,000 times height in meters is 0.2 times 10. So this gives us a total of 102,000 pascals. So this is the pressure of that gas. You can see it's actually higher than atmospheric pressure, which is 100,000. Coming to this other side, then the gas pressure will be atmospheric pressure, which is 100,000 pascals, minus the height column height difference gives us 0.2 times density of water times 10, which gives us a total of 98,000 pascals. So that's how we can use a U-tube manometer to determine the pressure of a gas when connected to it. So another application of transmission of pressure, especially for example this case here, this is a transmission of pressure in liquids, can be used in a hydraulic system where we have where the pressure comes from is called the master piston. So this is a piston called master. The one that receives is called the slave piston. This is the slave cylinder, master cylinder. Master piston, slave piston. So this is a hydraulic lift. If we put some luggage over here, then you will see it rising up. You can use it to lift objects up. So let's look at an example involving this hydraulic system. Here I have two hydraulic systems. The first one is a simple one which has both pistons on the same level. We have piston 1, which is the master, and then piston 2 is the slave. So in this case, a small force F1, which is 1,000, is multiplied to produce a higher force F2, which can be used to lift very heavy objects. So the reason why the force multiplies is because we can see the area 2 is higher than area 1. So we use a small force to get a higher force. So what happens is we have a ratio here. The ratio of force 1 to area 1 should give us the same ratio of force 2 to area 2. So F1 over A1 equals to F2 over A2. Substituting, we have 1,000 over 1 equals to F2 over 5. And the force 2 reproduced here is actually 5,000 newtons. So its area to the ratio in which area is multiplied is the same ratio in which force is multiplied. Here we have another setup. This is another hydraulic system which is not the same as the previous one. You can see the master piston is slightly lower than the slave piston. So actually it does the same work where it reproduces a small force into a higher force, because you can see the ratio of areas is actually more than 1. So the difference is that we have an extra liquid here which also participates in reproducing force 2, in the sense that on the right hand side we have to add pressure produced due to that liquid. So F1 over A1 equals to pressure due to the liquid plus F2 over A2. You must add pressure due to the liquid. So Substituting, we have 1000 over 1 equals to rho Hg plus F2 over 5, and the force we produced is 4000. So this one multiplies the 1000 newtons to 4000 newtons. This one multiplies it to 5000 newtons. So those are areas where we can use ratios in hydraulic systems. Now the next thing we're going to see is another application, which is the siphon. With me here I have a simple siphon. I'm going to use this tube to make a siphon. I have a container here full of water. Then, as you can see, it's slightly elevated from the bench. This is just to give it a higher pressure. When we dip in the tube, nothing happens, nothing comes out. However deep I push the tube, nothing happens. But then, so what is supposed to be done is we induce the liquid inside here so that it can accelerate the coming out of water due to the pull of gravity. Actually, we give the pull of gravity some power. Then also, due to the cohesive forces of water molecules, they're going to pull each other down there. So those are the two reasons why we have to suck first. So let's see. So as you can see, water keeps on coming out without any effort from our side. So this water will keep on coming out. You can see the volume in the jug. The water is going down. It reduces until it is empty. This is because the pressure here on this side where it's coming out is actually higher than the pressure in the jug. So you can see without any further pulling or pushing of water, it still comes out. So this process will continue until it's fully empty. So this is another application of pressure in liquids, and it's also used in pumping of water to the houses. You find that most of the water reservoirs are actually placed. So, thank you for watching the video. Make sure you subscribe to the channel, Mabonga Labs, for more insightful videos on physics concepts and science in general. Thank you.